Okay, so we'll start with our second speaker, Tomasz Placek from Jagiellonian University Cracow on branching and relativistic spacetime. Please.
Thank you very much for having me here. And the topic of my talk is whether general relativity is deterministic or indeterministic. Quite a few people in that room have worked on that question, but I'm going to revisit it because I've been developing a branching space-time theory which is devised exactly to that thing, namely to analyze determinism and indeterminism in spatio-temporal context, and to try to give a verdict about questions like that, the topical questions. And the relevance is that this theory describes a version of determinism and indeterminism in some rigor, but also it gives a branching style reconstruction of basic objects of some physical theories. So it appears that it's easy to apply it to the topical question. So my plan is to give you a crash course in branching space-time theory and then to apply it to relativity. The first caveat is that it's not the theory of physics, it's rather a theory of possibilities, and it could analyze various mathematical structures associated with physics, but it has, absolutely no say how these possibilities develop, how space-time emerge and the like. So the theory was launched by Newell Belknap with the explicitly stated aim to combine relativity and indeterminism in a rigorous theory. The format is that it's an axiomatic second-order theory with two primitive notions. These primitive notions are events and the precausal ordering. Then the BST structure can be isomorphic to Minkowski spacetimes, some general relativistic spacetimes, Newtonian spacetime, but strangely, classical sequential growth of causal set theory cannot be handled by BST. The precursor theory is branching time of Kripke and Pryor. The developers, Thomas Miller, Leszek Wroński, Anna Luz, and myself. The main book is the 2022 Oxford book. The present paper draws on my joint work with Joanna Luz. Let me start with dispelling two misunderstandings. The first problematic question is what exactly branches? And the answer is that if we think of branching time, the precursor theory, it's not time that branches. It's quite similarly in branching spacetime, it's not spacetime singular that branches. Better and intended meaning is that courses of events, scenarios or histories branch. And as in BT, histories have temporal aspect only, and in BST spatio-temporal aspects, there is this difference in terminology. Now, if general relativity identifies histories with GR spacetimes, then, the GR spacetime, plural, branch in BST. But beware, many BST structures do not admit spacetime, in any reasonable sense. More importantly, perhaps, is the second question, namely which determinism and indeterminism we are going to model. We are all accustomed to the global version of indeterminism, explained in terms of big things like possible worlds or models of a theory, and then invoking mappings between segments of possible worlds. But there is a different notion that is individual-based or local, and is openly modal, and it goes down to Aristotle's De Interpretatione. Here's the quote. Aristotle says, it's possible that this code may be cut in half, and yet it may be cut in half but wear out first. So in this vision, indeterminism is a fairly localized concept. It is in a region or related to some object, and this region or object has multiple alternative possible future continuations. Well, to the axioms of the theory, there are these two primitive notions, namely the set of point or possible point events, and they are ordered by pre-causal relation, interpreted as one thing can causally influence another one or can occur after another. So the first postulate is that the set with ordering is non-empty and strict partial order. Then, as in many modern metaphysical theory, the question is which events can occur together, which events are compossible. And here we come with the so-called later witness criterion, namely E1 and E2 are compossible if there is a later event that is in the future of the two. In other words, two events are compossible if there is a third event that the two could causally influence. Okay, so that's the notion. Then if we make the typical maximality move, we land with what mathematicians called directed subsets in the partial order. So histories or scenarios in BST are directed subsets with the motivation given by the later witness criteria. Some more axioms I mentioned. There is this axiom requiring that the density, that the ordering is dense. There are axioms relating to continuity, explained in terms of bounded chains. So non-empty lower bounded chain has an infimum. And here is asymmetry between up and down, namely, well, there is no supremum simpliciter for upper bounded chains, only there are history-relative suprema. So here is the picture. There are these two histories differing on the coloring regions, and here is a particularly located chain, and which is in both histories. It doesn't have a supremum simpliciter, but it has supremum in one history and in the other. That's a somewhat important picture because we'll soon come across problem Hausdorff property, and that's where this picture leads. Problems with Hausdorff property. So what I explain now is the core of BST. Now I didn't mention any branching, but well, there should be branching. Just by the idea that, well, an event has alternative possible continuation, and the BST structure is to represent everything that was, is, or will be really possible. So these two claims lead to the view that every two histories overlap, and then this overlap is downward closed. But then that brings us to the question, topologically speaking, how histories branch. And there are two options, namely, there is a maximal element in the overlap of the two histories. That's the first picture here. Or just the opposite, there is no maximal element. However, there are minimal elements in the historical differences. Now, if you look at that from the topological perspective, it looks like a hard choice because in the upper picture looks like having a problem with local Euclidean property. That's the problem. And the bottom picture looks like having a problem with Hausdorff property. Okay? Yeah, just to recall, well, first, well, to talk about this property, we need to have topology. BST comes with some topology, Barta topology. Here is just the repetition of what local euclidicity and Hausdorff property is. Well, we are interested in making a link to physics of spacetime. So we need local euclidicity. So we go for the option local euclidicity, but no Hausdorffness. And that's enforced by the postulate that I'm not going to go into that. Well, the picture that emerges from this decision is the following. The BST structure with more than one history is non-Hausdorff, but locally Euclidean. Moreover, it has bifurcating curves of the second kind. Just to say which are the second kind, the bottom one are the second kind. Okay? And luckily, each history, that is the directed subset in BST structure, is Hausdorff, moreover maximally Hausdorff, and also it has no bifurcating curves of the second kind. So that suggests a sort of topological criterion of historicity, which I do not enter. Now, there is a similar situation with respect to Hausdorff and non-Hausdorff differential manifolds. So with Joanna Lutz, we have that theorem, namely that any non-Hausdorff differential manifold consisting of a side atlas and metric can be constructed by gluing together maximal Hausdorff differential submanifolds of that manifold. So that's like a machine. Yeah? You start with the non-Hausdorff manifold, you decompose it, and you could compose it back exactly to that thing. And second, it's even more general, namely if you start with a family of differential manifold of arbitrary cardinality, then the product of gluing these manifolds is in general differential manifold. So that parallelness between, on the one hand, non-Hausdorff structure in BST and histories in BST being Hausdorff, and the situation in general relativity invites the following project. First, allow for generalized differential manifold, that is Hausdorff or non-Hausdorff, as basic objects of GR, though do not insist that these non-Hausdorff objects are spacetimes. Okay? Then, investigate maximal Hausdorff submanifolds of generalized differential manifold. And if it happens, it might happen that the decomposition into maximal Hausdorff submanifold will be BST friendly. That is, that decomposition would satisfy BST axioms. So that would be the evidence of indeterminism. However, as we'll see in a moment, there will be a problem with bifurcating curves. And also be aware that this decomposition into Hausdorff submanifold might be completely weird. Yes? There are no rules where the isometry obtains. Let's return, let me talk a bit about bifurcating curves. These two varieties. The first is uninteresting in BST, they just happen, and they are unproblematic in general relativity because, well, they could not be geodesics. Both in Hausdorff and non-Hausdorff manifold, we have local uniqueness results for geodesics. And so the first picture just violates this result, so it would not occur in general relativity. There is that second thing, which is used as a criterion of indeterminism on BST. And in the literature, you will find opposition to the bifurcation of that second kind in Holger-Ellis, Hajicek, and Ehrman. But on a reflection, that opposition stems either from opposition to indeterminism, that was Hajicek's point, or from seeing this bifurcation as happening in one world. But, well, that's not the intended meaning. There will be, well, alternative trajectories, so to speak. Well, let me get back to turn finally to general relativity. And we're talking about BST structure for relativity. The first warning is that there will be many weird BST structure, but there will be physically looking structure, like for instance, Minkowskian branching structure, in which histories are isomorphic to Minkowski spacetimes, but these objects are not backed by any physical dynamics. And there are also BST structures based on globally hyperbolic spacetimes, but for our purpose of analyzing indeterminism, they're not interesting because of the Choquet-Brouchard result. So, well, we are turning to strange objects, namely we consider extensions of maximally global hyperbolic spacetimes. And the question first is, does it have extensions? And then what extension? It's better they will turn out non-isometric. They should be maximal, and also ideally they should be to the future. We might consider whether we should insist on Hausdorff extension or non-Hausdorff, but to accord with that program of finding or decomposing non-Hausdorff objects, I opt for non-Hausdorff extensions. So the idea is to investigate maximal Hausdorff submanifolds of a maximal non-Hausdorff extension. The question is, are they isometric? Let's do one illustration, namely as the familiar object, the Taub-Knut spacetimes. The Taub spacetime has two singularities, well, signaled by T plus and T minus. That's, of course, southwards, Hausdorff and globally hyperbolic. And, well, here's the picture. Then we could extend it up. So here are the two extensions, that's up plus and up minus. They're isometric. We could also, well, there are they're closed time-like curves in the new regions, just to warn you. And here is another extension, namely the downward extension. Again, these extensions are isometric. However, if we combine up and down extension, we arrive at something similar. So that's up plus down plus versus up minus down plus, and they are non-isometric. Again, they have CCCs in the new regions. So the question is, are these so you might think of these as two Hausdorff manifold, or, well, my preferred way, look at that as non-Hausdorff maximal extension. Yeah. So, are they? Is this case the indeterminism in this local and modal sense? Well, first there's the technical problem, namely we have CCTs, And the order is here defined in terms of causal curves. So we have a problem that this ordering is no more asymmetric. So one needs somehow to develop BST a bit further, and that can be done. But there is some major conundrum, namely, there are no bifurcating curves of second kind in this Taub-Nuth construction. And there are no such curves in other constructions, like the extension of Gaudi polarized or extensions of Missler. And recall that for BST, these bifurcating curves of second kind mean indeterminism, to the point that, well, if there are no such curves, then, there is no local model indeterminism. Moreover, we have, by Clark in 1976 results, in maximal non-Hausdorff extension, there might be no bifurcating curves of the second kind, because that result says in non-Hausdorff spacetime it's either not strongly causal or admits bifurcating curves of the second kind. So these examples, these extensions that I mentioned, they all violated strong causality. So here's the definition of the bifurcating curve, namely that's two continuous curves such that they are identified below a certain parameter. One might wonder, when do bifurcating curves of the second kind exist? And the answer is given by Hajicek. The necessary and sufficient condition for non-Hausdorff differential manifold to admit bifurcating curves of the second kind is that the gluing is continuously extendable. I'll explain it in a moment, but first the concept of gluing. So we have these two manifolds, 1 and 2, and gluing is a function from the open subset of the first manifold to the open subset of the second manifold that is isometric. So gluing is isometric. Okay? Now, talking about continuously extendable, we say, well, there is that gluing working on two open subsets, and it's continuously extended if there are some larger subsets that are linked by continuous functions. So there is this phi prime here, excuse me, that is from the open set to the other open set. It's continuous, and its restriction to A, to the early set, is identical to the isometry. So in short, gluing must be an isometry, but the continuous extension need not be an isometry. So that's the thing to remember. Here's the picture why this continuous extension is enough to produce bifurcation of the second kind, but I'm leaving it. And well, back to the drama, there are no bifurcating curves of the second kind in the well-studied extension of Missner-Taub polarized Gaudi. Why is that so? Well, the gluing operations they are not extendable. For instance, in Taub case, the gluing map is singular. And well, here is my conjecture. I've been trying to prove it over some time with collaborators. We're quite close. So the conjecture says that in a reasonable construction of non-Hausdorff extension of a maximal globally hyperbolic spacetime, a gluing map is not continuously extendable. I need, to justify myself to that qualifier, reasonable or unreasonable. Also, unreasonable construction is when you glue together smaller regions that it is possible to glue. Okay, so it's like, you glue something smaller, and then of course you could extend it, but there is no, there is pretty arbitrary. Well, with that conjecture, let me sum up and say the conclusions. So the assumption, or the simplifying assumption of the talk, is that non-Hausdorff or differential manifolds are respectable objects of GR. I'm saying it without committing myself to identify these objects to space-times. Then, here's the conjecture, namely that the reasonable non-Hausdorff extensions are not produced by continuously extendable gluing. That it follows by the Hajicek result that this reasonable non-Hausdorff extension of maximal global hyperbolic spacetimes, they do not have bifurcating curves of the second kind. But just recall, the existence of bifurcating curves of the second kind is a necessary condition for local and modal indeterminism. So you have multiple histories in this framework only if there are bifurcating curves of the second kind. So the final word here, GR, it's not indeterministic in that specific Aristotelian sense, that it's not locally or individually based and modally indeterministic. I'm leaving the meaning and the possible interpretation to these results to the discussion. Thank you very much.
So thank you very much, Tomasz. It was extremely interesting and dense for me to go through presentation and the book.
With the emphasis on dense.
Yeah. So, being this very new to me, I'll try to make sense of the presentation and then I'll ask you some questions. So, at least ever since Adamas was put in this criteria, we know that determinism seems to be quite a friendly environment in which to develop our theories. So according to Adamas, well put in this criteria, the problem is well posed. If it has a solution, the solution is unique and it varies continuously with respect to initial condition and parameters. So of course, the theory of framework is friendly in the sense that we may expect, given certain conditions, to provide successful predictions. But of course, the goal that we are also trying to reach is to ask ourselves whether this notion of determinism, either being taken as a framework to think about physical reality or physical reality itself, is sound. So the question that Tomasz was, I think, very interestingly illustrated is whether we have motivations to think that there may be genuine notion of indeterminism. And the way in which this project is carried out, I would say, can be divided for the sake of simplicity in three main steps methodologically. So the first one, we can take it as a definition of indeterminism, and of course we can have local or global definition, but overall the idea, if I got it right, is that of having some form of non-uniqueness. So a system's evolution is indeterministic if it can have possible alternative continuations. The second step in the methodology is to adopt a specific formalism to try to ask if this notion of indeterminism is at stake, and the proposal by Tomasz and colleagues is to somehow adopt the legacy of Linda and to adopt this branching space-time formalism in order to tackle the notion of local and modal indeterminism. So inspired by Aristotle's way of framing the notion of determinism. And the third step, which I guess is the one that we're really interested in, especially here, is to look at specific theoretical frameworks such as general relativity and ask ourselves whether through this formalism we may spot this notion of indeterminism. So I guess my question may sound very naive, very broad, but I will just ask something about these three steps methodology, the way by which I put these three steps methodology. So the first, I would just simply call it as definition of indeterminism. And so I guess my question would be, first of all, why do you think that there's good reason to focus on the modal and local form of indeterminism with respect to global versions, broadly speaking? The second concerns the very, let's call it formalization. So the specific formalization we are adopting in order to evaluate whether a certain theory is indeterministic or not. And the reason why I'm asking this is because these branching space-time formalism is very rich, very complex, at least to me. And from the presentation, I was not sure whether I completely understood how much already temporal this branching space-time structure is, in the sense that at a certain point you outlined that there's no one-to-one mapping. We can think about like many forms of mapping between this branching space-time structure and specific physical theories. So I was wondering, so on the one hand I thought this, on the other hand you explained that the prerequisites of this formalization leads us to think that two events, say E and E first, that we take as primitive, are related by this pre-causal ordering. In case E first is after or is successive, somehow use the word future of E. So I was wondering how much this formalization somehow is already biased with respect to evaluating indeterminism in general. And then the third question would concern what we may call the physicality of the solutions we are looking at. So of course we do have motivations to think that the global sector of GR does not cover the full spectrum of solutions. And so I was wondering how much this should be relevant in evaluating genuine form of indeterminism, and this I think would apply to the globally applicable solutions and as well to child space-time and business space-time. So it would be great if you could elaborate a bit on which kind of information we should get from this kind of, from focusing on this specific class of solutions. And so the question I guess would be, we may have been biased against alternative possibilities, we may have been biased with respect to how deterministic distributions should be and how physically we should take them to be. Thank you.
Thank you so much. Thank you. So starting with the definition of determinism, it's in history there are simply these two approaches to determinism. One starting from Aristotle with these clear model undertones, and the other evolving from Laplace. In my early education, I was struck just having a postdoc in Pittsburgh that you change the floor in the cathedral of learning, and you change the landscape. I mean, there are those people doing modern logic or theories of agencies that work with Aristotelian determinism, and you go to Herman and Norton, and they work in a completely different tradition. So I think that both these approaches are legitimate. They both need to be specified, and well, that was my main idea when I want to look at the Aristotelian version. Besides, well, in this, I have one worry with sometimes we want to know, well, if there is an indeterminism, where is it located? What is this indeterministic process that makes the whole thing indeterministic? And typically this global approach leaves these questions on us. So that's my handling of the definition. Formalization, that the main issue, if I remember, was the ordering. Yeah, so just to say again that ordering X is below Y if and only if X can causally influence Y. That's the meaning. And, well, the job is done by the assumptions like, well, that's partial order density continuity and the like. So that's this pre-causal ordering, and the whole drama of emerging time, of emerging space-time, happens on the second stage. Namely, mathematically, you postulate that there is some structure, some higher structure. Well, and you ask whether it's isomorphic to Newtonian time or to Minkowskian space-time and the like. So, how exactly that change from this pre-causal ordering to this spatial temporal feature, how does it happen? We don't have a clue. That's for physics, not from the framework for possibility. And the last question, physicality of solution. I'd rather turn to criteria of physicality at some later stage. Just trying first to understand or to defend indeterminism without any assumption that somehow bias the answer towards determinism. But at the end of the day, that's an important question, whether the GR solutions are physical. So it's more like a question of priorities in my case.
Thank you.
Thank you very much. One question I have is about the status of the branching spacetime theory. You said at the beginning it's not a physical theory, so I'm sort of trying to understand what exactly it is. And let me try to give you an analogy. So in the metaphysics of time, there are people who think that time must be atheoretical, based on some considerations about what time is, what the essence of time is, that they think is correctly captured by an A theory. And they say it's not a physical theory, it's a metaphysical theory about the nature of time. And then we discover that A theories of time are incompatible with relativistic physics, say. And we come to the conclusion, okay, the physical time cannot have the features that seem to be required by an atheoretic metaphysics of time. And that leads us to the question, what's then the status of this atheoretic metaphysics? You know, does this capture somehow the fundamental nature of time? And here too, so in branching space-time theory is a theory of agency, maybe, of human free capacity to act in certain ways, some sort of capturing a modal indeterminism, an Aristotelian kind of sense of that. Then we look at general relativity, giving us the nature of physical spacetimes, which you then discover is not compatible with branching spacetimes. Now, what is branching spacetime theory about if it doesn't match somehow the spacetime structures postulated by GR? So what's the status? What should we make of that?
But can you tell me more why you think that it does not match to relativism?
Well, because if GR is not locally and modally indeterministic, and it seems to me that branching spacetime is exactly a theory that sort of seems to require that. That's the whole idea of trying to model that.
No.
Or maybe I misunderstood.
No. Well, it's a general theory of how this world could develop, say, from some event zero. And it might have various alternative scenarios, but it does not destroy the theory if it turns out that there is just one scenario. Okay. So one understanding of that result is that, well, GR is not locally modally indeterministic. Well, we end up with a trivial branching spacetime theory that has exactly one spacetime. Okay, so the theory is somehow open to all sorts of extremes. Yeah, one extreme is exactly one history. And well, the other extreme would be umpteen number of histories. Well, every point is the Champéry point and so on. Yeah,
That's very helpful. Thank you.
Yes, on this conjecture, there was something you said that I didn't quite understand. You said that you think the conjecture fails because you won't have bits that are small enough to glue. But I thought that in GR that you would have bits of arbitrary smallness because you can just dial up the granularity as much as you want.
Okay. So you are referring to that concept of reasonable non-Hauser extensions do not have a bifurcating curves. Okay, so that is the consequence of this one. And the conjectures that they are not produced by continuously extending gluing, and that conjecture and the work is done here by this reasonable thing, namely, we could ensure that the gluing is continuously extendable just by not gluing enough. Okay, so we have these isomorphic open subsets here and there. We could glue them. However, fearing the problem with the continuous extendability, we do not glue them fully. Okay, so there are some remnants here and there, and that allows the continuous extendability. But that looks to me like cheating. Okay, so somehow, well, you arbitrarily decided to glue the manifolds in a strange way. I don't know whether I'm addressing that.
So just go back to the slide where you talked about the conjecture. You said this thing about the bits being too small.
Okay.
Yeah, you said glues together smaller regions, then it's possible to glue. And I just don't understand. Like, if we're in the mood of extending space-times, like, what does this mean? Because it looks like we just have regions that are arbitrarily small. So why can't we just glue those?
The instinct is to glue as large isomorphic region as possible. So And then, well, my conjecture says that if that's the way, then you could not continuously extend it. The conjecture is based on, well, looking at these particular cases, that there are some singularity and really you could not, extend it. But what however, you could escape the conjecture just by forgetting reasonable, and instead of gluing them big guys, you pick some pieces of them. Okay, here's the one, here's the other, okay, you glue them. And then, of course, you could extend the gluing in a continuous way.
I see, but you think that those aren't reasonable.
Yeah, then I find it unreasonable because I do not have an answer why didn't I glue the large objects, but I glued some smaller substances.
What is it to be reasonable? Like, what are the constraints of reasonability here? So when you say that it's unreasonable because like you've got those larger things that you could do, why? I think I'm just not understanding what you mean by a reasonable construction.
Reasonable means glue as large isometric objects as possible. Otherwise, give me an explanation why you are gluing smaller.
I think I want an explanation for why we glue.
Wow. Well, that's what the mathematical structure is. There are those isometric regions ready to do. But well.
Yeah, thank you. It was really interesting. I guess the other question goes back really to something that you said at the start, which was quite puzzled when you presented two possible ways of thinking about the branching, and you say either we have a Euclidean but non-Hausdorff manifold, or we have a Hausdorff but non-Euclidean manifold, and you go for the Euclidean but non-Hausdorff option. And I was kind of surprised because, as far as I know, there is a rather well-developed literature of how to deal with with branching non-Euclidean but Hausdorff in practice manifolds, which basically solves in practice the problem we have here. So what you find, the example that people always use is something like a pencil diagram, right? Like which is exactly like the branching, like what is the branching into.
So you do dialectics instead of branching this terminology.
No. You have like one trunk that then splits. Like they just split the pens because they take a circle instead of a point. But if you at a point, it would just look like one line that then splits in two. And naively, that's singular, of course, as you also get in this. But what you can show is that you can regularize this by basically at a singular point introducing a small region where the metric becomes complex. And then it goes through continuously perfectly fine, and I would assume, even if I haven't seen a proof, that you would get exactly those bifurcating curves of the second kind, because at the end of the day you just need to basically go across a complex metric, and complex metrics are lines, like topologically there's nothing too weird about them. It's just there's the complex number is a real one. And then there's you can even look at quantum field theoretic extensions of these because people have worked them out even in that context because they happen to be relevant in some situations.
Let's escape it. Well, we were somehow focusing on those simple, partial theoretical structures.
Yeah.
And of course, if you add matrix and some beautification.
But then what I assume it should give you like a GR space-time in practice, something that solves. Well, I don't know if it exactly solves the Einstein field equations, but let's say something that has like a Lorentzian metric, like a fine object for GR, then nevertheless has this stuff. I think, again, I don't know exactly.
On the same page, the result would be the local Euclidean structure with Hausdorff property.
It would be locally Euclidean everywhere except the bifurcation point because it becomes complex there.
Okay.
So you
But
could take the other.
that wouldn't be problematic from the physical point of view.
No, that should be fine. There should be no divergence there. At least people do exactly these constructions and then they try to figure out when it's possible and when it's not. Like it's topology changing space-time.
So I find it very interesting how the special tempo structure and the model structure interact, like they're very closely intertwined. Let's put it like that. So in branching time theories, right, usually have just times nearly ordered, and then if they branch, then these are different histories, right? So you can, if you have two times, then just looking at these two times, you can know whether they belong to the same history or not. And they do if the one comes before the other, and they don't if not, right? They don't know. And now in the branching space-time theory, if I understood it correctly, it's not so easy because whether two events are composable depends on whether there's something in their common future. So it's not something that is decided locally in some sense. And that's interesting, I think, also metaphysically speaking, right? That yes, it depends on something far away in the future whether two events belong to the same possibility or not. So I was wondering if that's correct as an interpretation, and yes, whether you can say
that's correct. So agree, that's strange. It appears that a possible world or a possible history, it's a familiar object. I mean, it's like our room, but well, much larger. Okay, and this line of thinking pushes in the direction that it's not so simple. Okay, we could relatively easily decide about some little events whether they are composable, but to get to the totality, well, it's very complex. And I had just a paper with a logician friend of mine that pushes in that direction even further. Namely, if you do that construction, in many theories, not only PhD, you do that construction, start them with the notion of composability, and then produce the maximum option. Then, typically, you need axiom of choice. Okay? And, well, most of the objects you will produce will be the so-called intangible objects of mathematics. So objects that you could not display, you could not give an example. Yeah? So, well, so that's the landscape. I think we are. It's not just the feature of BST, it's a general feature of modern metaphysics. These objects that we so easily talk about, possible worlds or possible histories, oh, they are crazy. Most of them are crazy. Most of them you cannot illustrate. So to give an example, this intangible object is, for instance, maximal filters in partial orders. So most of them are intangible. Thank you for that.
Yeah, I think it was also very interesting. That we follow this quite a bit also the work of Joanna. And so I was just wondering, how much sympathy do you have to perceive of this branching theory as a kind of modeling framework for also, let's say, modeling branching of space-time towards more quantum? Or do you think such a project is somehow not at all sensible?
is some literature 20 years ago.
Okay.
But so that's also we play with geography.
Okay, that's
So we grow in the direction. We need, but to have a nice result, you need to focus on indeterministic interpretation. Otherwise, it would collapse.
Yeah.
Single.
What about, I mean, also like superposition of space-time itself, so to speak. You say GW sounds like, so to speak, superposition within the space-time, right? But say you have masses, and it's like what I asked in the previous stuff, and each mass gravitates, so to speak. So you get branching, so to speak, the masses, but then also basically with a different space-time, so to speak. Is something you
That could be handled, as I said. There is no obligation that histories meet space-time. There is no obligation that they meet the same space-time. So things like one space-time in one history and another space-time in the other.
Okay. So you have synthesis for such. You would do. I mean, this is interesting thing to do with this framework, right? Okay.
Yeah, so as a matter of fact, many of us have been thinking about causal set theory from different angles, but we've been told in certain occasions that it's a minority view and we should not be focusing much on that. And at a certain point you were saying that indeed branching space optimization seems not to be compatible with the...
Yeah, that was a surprising result that my former PhD student and myself. Okay, it's similar to your results. So the problematic feature is that this classical sequential growth path, this CSG path, that they reconvene. Okay? And this reconvening is massive. And that's very much against the axiom of this. This theorem that if some histories branches, then they will never recover. So that's the point of contention between views here and puzzle.
Should this be another motivation to think about the set theory? Or?
I don't know.
Thank you.
Thanks. So I was wondering about two things related to the nature of events in this theory, of branching set theory. So, because you expressed at a certain point, which was a bit surprising to me, that branching space-time need not be interpreted even as a region, or at least not as a space-time. I don't think like the usual interpretation of like just taking an event to be some kind of space-time point works. So it needs to be something else. But then relatedly, like surely these events are not extended in any way themselves, right? So I was wondering like what type of properties do these events have of this branching space-time? So what type of features do they have in and of themselves? And then related to the extended object, my worry was a bit related to Annika's. Namely, if you have extended like objects, surely I am an extended object like this. Is it true that like the fact that I am here and like extended in this way also depends on, well, maybe like the future? So it's not even like whether something is composable, but even like just extended object or extended events or whatever you want to call them. So those are my kind of two interrelated questions. So about like what should I think about these pointwise events and how should I think about the extended events or objects?
Extended is easier. This is the case of your body, the crossroad. You always have some later events that somehow always after all molecules and so on.
Yeah, so like metaphysically that's a bit strange to me that like in a sense like the fact that I am here now, which may be hopelessly naive to many of you here, but like is in any way like dependent on like first of all, modal structure, and second of all, like modal structure in my modal future and not in my modal past, which is like strange. But then, like, what are these points? Like, what are the properties of these points? If I'm not to interpret them as like space-time points with like the usual features of space-time points, like what type of features do they have?
Well, quite generally, they are just vectors of properties.
Yes, and so my question would be like, what type of property? Like what like they don't have charge or something like that? Like they don't have.
They could like some field properties or charge with the light.
Okay.
Yeah. So if there were not that one thing with causal sets, a closet would be an example of that.
Just like the usual particles of physics are presumably extended on this theory, right? So like any like properties like charge are presumably only features of these extended groups, but then the points, because they are, yeah, unless there are also these theories where like the minimal points are not like points even, but they are themselves already. I'm a bit puzzled, but maybe.
Okay, so didactically you always begin with talking spatial temporal points or minimal events in our world. But then you say that, well, it's really minimal. What's important is that if there's properties. What properties? Well, an easy move is to go to the 19th century field theory that says, well, that there are various field properties like electromagnetic field.
Okay, I would have to read more about it, but thanks.
Okay.